Hello all, I'm back with another video, and this one is on Unit 6, Practical Skills in Physics 2. So it's from the International A-Level curriculum. I believe this exam is taken the 10th of June, so in a few days. So hopefully it will be helpful to some people. Let's dive in. I don't have too many things I want to discuss, except the usual thing I always say. This test is an hour and 20 minutes. So 80 minutes. So try to spend there are 4 problems, but they have varying marks. So for example, if a problem awards 15 marks, try to spend about 15 minutes on it, just so you stay on time. And let's just start. So question 1, the electrolytic capacitor shown can be used to store energy. A student connected the electrolytic capacitor into the circuit below. Okay, and we see the circuit. State 2 safety precautions the student should take when connecting and using the circuit. So these capacitors have to be connected with the right polarity, meaning that the positive, for example, needs to be here and the negative here. Otherwise, they break down. So that's the first thing we want to write. So let's write that down. Connect the capacitor with the correct polarity. As electrolytic capacitors are polarized. Okay, and here polarized means that they have a preferred side that has to be positive and a preferred side that needs to be negative. So electrolytic capacitors are polarized and can be damaged in reverse polarity. So that's the first thing we need to take care of. The second thing is that I do not exceed the working potential difference of the capacitor, as this risks breaking down the dielectric. Okay, and let's create another new page, excuse me. And the last thing, okay, they ask for 2, so just write 2 of these 3, okay? But since this is kind of like a lesson as well, I'm providing more information than needed. So the third one is to ensure the capacitor is fully discharged, okay, before using. So ensure the capacitor is fully discharged, okay, before handling, okay, as it can store energy or charge, so it can store charge even after the switch is closed. Okay, so let's move on to question B. Okay, so the student used the switch in position 1 to change the capacitor. Okay, so what did I say? To charge the capacitor. Excuse me. What's wrong with me? Okay, it's a Saturday morning, guys. So I'm a bit sleepy still, I guess. So okay, with switch at position 1, you charge the capacitor. Okay, that's right. And then if you put the switch in position 2, I guess, then the capacitor will discharge through the motor. Okay, so let's go back. So the student changed the switch to position 2 to discharge the capacitor through the motor. As the capacitor discharged, the motor raised the small mass m through a height h as shown. Okay. The student used a meter rule to measure h. Describe an accurate method to determine a single value of h. Using a meter rule, you may include additional apparatus. So let's write down that you have to clamp the meter rule, the meter rule vertically, okay, next to the mass, okay, using a stand and a clamp, okay, and use a set square, okay, or spirit level to confirm it is truly vertical. Oops, okay. So that's the first thing. The second thing is to position the meter rule as close to the mass as possible, okay, to minimize parallax error, okay. And I will need extra space to write the third thing, so read the rule perpendicularly, so perpendicularly, okay, to the square, and also let's write eye level, okay, or use a set square and place it, so or use a set square placed against the rule to read off the height accurately. Okay, so that's the answer. Let's move on to the next part, part C. The student repeated the procedure in B several times. She recorded the following measurements. Calculate the mean value of H. So we have to sum up. So let's write it like that with a bar meaning the average. So H bar is the sum of these 4 measurements divided by 4. Okay, so the result is 0.242 meters. So 0.242 meters. Okay, part 2, determine the percentage uncertainty in the mean value of H. So first of all, we need the absolute uncertainty. So the absolute uncertainty in the mean height is equal to the half range, which we find by subtracting the 2 extremest values and divided by 2. So 0.246 is the largest minus 0.239 is the smallest over 2. So this yields 0.0035. Okay, that's the absolute uncertainty. And now the percentage uncertainty in the height is equal to the absolute uncertainty in the height over the height itself times 100. And this yields 1.45%. Okay, part 3, determine the efficiency of the electric motor. And they give us the maximum potential difference across the capacitor, the capacitance of the capacitor, and the mass of the thing that we lift. Okay. All right, so first of all, let's find the energy stored in the capacitor. Let's call it W. And since we are given the capacitance and the voltage, you can use 1/2 CV squared, which is also in the back of your paper. That's a thing that I always say. Do I though? When you take these tests, it's good to be aware that they have all these formulas in the back. So in case you get lost or you forgot about something, you can always find it here. So let's see. Yes, so this is what we are using, for example, right now. Okay, now let's go back and calculate. Okay, so this is equal to 1/2 4,700 times 10 to the negative 6 times 36, and this is equal to 0.085 joules. And now the GPE is mgh, so the mass is 20 grams, so 0.02 times 9.81 times the height, which is 0.242, and this yields that the GPE for the mass, I mean the energy needed to lift it from the floor to a height h, is 0.048 joules. And now let's use a clean page. So the efficiency is defined as the useful energy over the input energy, okay, times 100. The useful energy is the energy we take out of from whatever the machine we are using is. In this case, the energy we get out is the energy needed to lift the weight. By the way, why does that thingy pop up in the bottom of the page? Let me try to fix it. Writing aids, no. Okay, I don't know why it does that. Check spelling. I don't know. So anyway, so the useful energy is 0.048 and the input energy is 0.085 times 100, and we get the efficiency as 56.7%. Okay, and this was problem one, a little bit longer than usual, but I think doable. Okay, let's move on to question number 2. Okay, question 2. A student investigated the flow of water through a horizontal pipe using the apparatus shown. The mass m of water leaving the pipe in a time t is given by the formula, and we see the formula right there. And we're given where rho is the density, p is the pressure difference between the ends of the pipe, okay, r is the internal radius of the pipe, eta is the viscosity of the water, and L is the distance between digital pressure gauges. Show that the formula gives the units for eta, the viscosity, as n times seconds over meter squared. Okay, so let's take this formula and solve for eta. So eta is pi rho, and then the pressure times the radius to the fourth times t, which is time, over, let's see, 8 times the mass times L. Okay, and if we use units, rho has units of kilograms per cubic meters. Then we have pressure, which is of course pascals, okay, which we will later convert into newtons per meter squared. Okay, radius to the fourth, meters to the fourth, right? The units for time are seconds. And then in the denominator, we have kilograms for the mass and meters for the length. Okay, so let us think. So first of all, the meters cancel because we have, let's use the same color for the same unit. So meters to the fourth cancels with meters to the third times meters, which is also meters to the fourth in the denominator, so everything cancels. And also let's use purple to delete kilograms. So we are left with pascals times seconds, okay? And pascals are newtons per meter squared times seconds. So we can write this as newtons meters to the minus 2 times seconds. And we proved what they asked. So let's move on, part B. The student used a meter rule to measure L and a stopwatch to measure T. He adjusted the water tap to give a constant flow of water. Describe a method to determine an accurate value for eta. Your method should use a suitable graph. Okay, and this is a 6-mark question. Okay, and with writing questions, I forgot to mention it in the beginning of the video. When a question awards 6 marks, like in this case, we have to generally provide 6 sentences that justify something or describe something. If a question awards 2 marks, 2 sentences are enough. So anyway, let's go find those. Do I have 6 sentences here? We'll see. So let's start answering this. I will need extra space as usual. So let's start from the formula. So from the formula, mass equals to pi rho pressure r to the fourth times time over 8 times the viscosity times length, comma. We can see, okay, we can see m is proportional, okay, is proportional to t, comma. So plotting m versus t gives a straight line, gives a straight line through the origin, okay, with gradient equal to pi rho pressure r to the fourth over 8 eta L. Okay, so this works, right? I mean, if we plot mass versus time. Now let's go see what we will need to do that. So first of all, we will need to measure all these quantities over here. So this, that, etc. Okay, so let me encircle that and start writing. So and you see how these questions, once you grasp the physical understanding of what they ask you, then you just have to describe menial things. So for example, the first thing we will write is that you need to measure the internal diameter of the pipe, at several orientations, okay, and find the mean, okay. So R, which is equal to D over 2, is accurate. Okay, let me use extra space. Now, the second thing is to use a spirit level, okay, to confirm the pipe is horizontal, okay. And we can write in parentheses, so the pressure from the gauge is reliable. Okay, so we really need this to be straight, so the pressure is reliable. Okay, now the next thing is to turn on the tab, okay, and wait until the pressure difference, okay, is constant before starting measurements. Okay, now the next thing is to record the mass, of water collected and the corresponding time for at least 5 different values. Okay, so you have enough data points for the plot. Then the next natural step is to plot mass versus time, okay, and draw the best fit line, okay, and then finally find the gradient, which is oh no, it's not equal, so find the gradient, use it to find eta, which is going to be equal to pi rho p r to the fourth, okay, over 8 times the length times the gradient, okay. Actually, let me simplify that. So 8 times the length times the gradient, okay. Okay, part C, the mass balance can be connected to a data logger. The data logger records the mass shown on the balance. Give 2 reasons why using a data logger would improve this investigation. So let's write down that the data logger records mass and time simultaneously. Okay, removing, let's put a comma there. So removing the reaction time error. Okay, and the other thing we can write, maybe we'll use the extra space again. So actually we need extra space. Okay, so let's go here. So, and the other thing is that the data logger, okay, has a high sampling rate, high sampling rate, comma, capturing many more data points than a human observer could record manually. Okay, question number 3. A student investigated the rotational oscillations of a mass on a spring using the apparatus shown. When the mass is displaced, through a small angle, the mass performs rotational oscillations about the vertical axis through the spring. The student used the stopwatch to determine the time period t of the rotational oscillations and describe how the student should determine an accurate value for t. Okay, so time a large number of oscillations. So time a large number of oscillations. Okay, so 10 or 20. Okay, using the stopwatch. Okay, then divide by that number to get t, reducing the effects of reaction time errors. Okay, so there's more. I'm sorry, guys. Lately, I think I write too many things. But anyway, use a reference marker. So use a reference marker. Okay, at the equilibrium position. Equilibrium position. Okay, of the oscillation to define, excuse me, a consistent start stop position for each cycle, I guess. Okay, and finally repeat the timing and calculate the mean value of t. Okay, and allow the oscillations to settle before timing. Okay, let's move on to question B. The student predicted that the relationship between T and the mass m was of the form T equals to A times m to the B, where A and B are constants. Explain how a graph of log T against log m can be used to determine the value of B. Okay, let's take the log of both sides. Log of T is equal to log of A plus m, plus B times log of m, okay, which is of the form y equals to some constant times mx. Okay, so the gradient is equal to B and the y-intercept is equal to log A. Okay, I mean, they didn't ask for that, but I just wrote it down. Okay, so this is the answer. Let's move on to the next part. Okay, part 2, the student varied m and determined the corresponding values of t. She recorded the data shown, I guess. Plot a graph of log t against log m on the grid opposite. Use the additional columns for your process data. So we will actually need log of m, okay, in kilograms, and log of t over seconds. Okay, I'm gonna write the first pair and then I will speed it up. So minus 0.69, and 0.16. The next point is minus 0.52 and 0.27. And anyway, let's speed this up. Okay, these are all the values. Let's move to the grid and start plotting. Okay, first of all, we see that all these values for log of m are negative. So we will do the graph a little bit different than usual. So let's start with the x-axis, which is going to be this one. Okay, and here we have log of m, and the vertical axis is going to be there. Okay, and the reason is, oops, no, we will need more space. Let's put it over here. Okay. Right, so this is going to be our log of t. Okay, is that visible? Okay, let's move it over here. So log of t. Okay, so the range goes from about minus 0.1 to minus 0.7. So steps of minus 0.1 are good. So we will actually start from 0. So that's going to be our 0. So let's make this minus 0.1, minus 0.2, minus 0.3, minus 0.4, 0.7, 0.6, and 0.7. Okay, I hope you can read it. I'm sorry, but there is not enough space. And then for log of t, we see that we go from about 0.15 to about 0.50. So we will take steps of 0.05. Let's make sure that we have enough space though. Okay, so let's start with this is going to be 0.15. So 0.20, oops. So 0.25, 0.30. I think this looks good. 0.35, 40, 45. And we said we need up to 50. Okay, so 0.50. Okay, I hope this is comprehensible. So let's plot the first point, and then I'm gonna speed this up. So we have minus 0.69 for log of m and 0.16 for log of t. Okay, so log of t 0.16. So this is, let me think. So each of these little squares, okay, that little square is an increase of 0.05. So 0.016, sorry, 0.16 is there, okay, because 0.15 is this point. So that's 0.15, okay? So 0.16 is shown right there. And we need minus 0.69, which is this point, right? So that point is our first data point, I think. Yeah, because here we have an increase of 0.1 between these large blocks. So that's 0.1. So every little tiny square is 0.01. Okay, so I hope this makes sense. If it doesn't, ask me in the comments and I will provide better explanations. But anyway, actually, let me show you one more and then we will speed up. The second point is minus 0.52 and 0.27. Okay, 0.27 is this point over there, okay? And then we need minus 0.52, which is actually, sorry, that point is the one we are looking for. Okay, let's speed it up now. Okay, so this is our data points. Now let's fit the line of best fit. Okay, so this would work, I guess. Okay, it passes through almost all the points. Yeah, I think it's good enough. Okay, we have these 2 points that are not exactly, I mean, that one and that one are not exactly on the line, but that's good enough. Okay. Yeah, I think that's it. Let's move to question number 3. Determine the gradient of the graph. So the gradient is equal to delta of log t over delta of log let me think, M, right? Yes. So we will use the extreme points, so the first and last, okay? They are on the graph, so we can use them, but you can use any 2 points of your liking that lie on this green line, okay? So 0.46 minus 0.16 over minus 0.15 minus of minus 0.16, and this yields 0.56, which is, let me think, this is actually B, okay? Okay, which is, so B is 0.56. They don't ask for it, surprisingly, but yeah, that's what it is. And then 4, determine the value of alpha. So let me think if we can actually do that. So yeah, that's the 0 of the graph. So actually, earlier we had to extend this a little bit. Okay, so all right, so you see that it touches, so that will be 0.6. So that point over there is going to be 0.6 minus, so 0.595, something like that. Okay, because every little box like this one is actually an increment of 0.05 in log of t. Is that right? So wait, I made a mistake. I'm sorry. This is actually, sorry. This is actually 0.55, excuse me. Therefore, that point over there is 0.545. Okay, that's the answer. So that's the y-intercept, and we can use it because that's the 0 of log of m, right? Yes. Okay, so it works. So let's write it down. So log of a is y-intercept, which means that log of a is 0.545. So a is 10 to the 0.545. So this is equal to, let me calculate it really quick, 3.51. Okay. Your answers may differ depending on how you plotted this graph, but okay, that's the answer. So let's move on to the next question. Okay, question 4. A student made measurements of the plastic protractor shown. Okay. Question A, part 1. The student used a micrometer screw gauge to measure the thickness T of the plastic protractor. Explain one technique she should use when measuring T. So, first things first is to repeat measurements of T at different positions, okay, across the protractor, okay, and calculate the mean, okay, to reduce random errors from surface irregularities. Okay, I will need extra space. The other thing is to check for and correct zero error before taking readings. Okay, to eliminate a systematic error from, to eliminate actually systematic errors from the instrument. Okay. Part 2. The student determined a value of TS 1.41 millimeters. Explain why a micrometer screw gauge is an appropriate instrument for this measurement. Your answer should include a calculation. So, the micrometer screw gauge has a resolution of 0.001 meter. Oops, what am I saying? Of 0.01 millimeters. How do we know this? Because it can measure T to 1.41 millimeters, so down to 0.01 millimeters of resolution. Okay, so the absolute uncertainty in T is the resolution over 2, which is 0.005 meters. Okay, therefore the percentage uncertainty in T is 0.005 over 1.41 times 100, which is 0.35%. Okay, so this makes it appropriate because let's write this down actually. So the percentage uncertainty in T is small, making the micrometer, an appropriate choice. Okay, so that was part 2. Let's move on. Part B, the student determined the volume V of the plastic protractor from the measurements shown. The student recorded the following measurements. The diameter is 10.1 centimeters plus or minus 0.05 centimeters, X and T as shown. Show that V is about 6.2 cubic centimeters. Okay, so we have to write down, so the volume will come from two parts, from this rectangular part and this, let's use a different color, and this circular path, okay? And in both cases, we have to multiply the area by the thickness to create a volume, right? So for the circular, the semicircular part, we know that the area is pi d squared over 4. And then we have to multiply by the volume, but we also have to divide by 2 because that's a semicircle, right? Okay. And then for the rectangular part, we have to multiply the diameter times x times t. Okay. So let's use a clean page to perform this calculation. So we have pi times 10.1 squared times 0.14, and this is cubic centimeters, and we have to divide by 8, okay, plus the rectangular part 10.1 times 0.45 times 0.14 cubic centimeters, which yields 5.61 cubic centimeters plus 0.63 cubic centimeters. So the volume is 6.24 cubic centimeters, which is very close to 6.2 cubic centimeters as requested. You might be wondering why I did this separately, and you will find the reason in a moment. Okay, so the short answer is that we will need those to be separated to calculate something. So let's go to part 2. Show that the uncertainty in V is about 0.2 cubic centimeters. So they ask for the absolute uncertainty, okay? But the formulas we used to calculate the volume involve multiplication, meaning that we can only find the percentage uncertainty of something that is multiplied and then convert the percentage uncertainty to absolute uncertainty. And we have two parts that we need to take care of. We need the percentage uncertainty in the quantity pi d squared t over 8, which will probably now answer why we kept those two calculations separated, okay? And the percentage uncertainty in that quantity is, we ignore the constants completely, and we need the percentage uncertainty in, in d squared. When physical quantities are multiplied, the percentage uncertainty is added, okay? I have a separate video on uncertainties, you should check it out. If I forget to put it in the description, search my channel and you will find it. So we have the percentage uncertainty in d squared plus the percentage uncertainty in, what's wrong with me today? The percentage uncertainty in t. Okay, and then the percentage uncertainty of a power is 2 times the percentage uncertainty of the quantity itself. Okay, so plus the percentage uncertainty in T. Okay, now let's plug in numbers. So 2 times 0.05 over 10.1. They give us, I'm using the absolute uncertainties they give us, okay? So 0.05 is the absolute uncertainty in D, which I use over there, times 100, plus the percentage uncertainty in T, we will need this 0.02. So 0.02 over the measurement, which is 1.40, times 100. And this yields 2.42%, okay, for the percentage uncertainty in the first volume. Okay, and let's turn the page here and actually calculate. So this is part 2, guys, okay? And we will also need the percentage uncertainty in the second volume of the rectangular area. So the percentage uncertainty in D times X times T is, you probably imagined it by now. So the percentage uncertainty of things that are multiplied is equal to the percentage uncertainty of the individual quantities summed, okay? So percentage uncertainty in D plus the percentage uncertainty in X plus the percentage uncertainty in T. That's a plus, not a T, I'm sorry. Okay, so let's put the numbers in. 0.05 over 10.1 times 100 plus 0.1 over 4.5 times 100 plus 0.02 over 1.4 times 100, that's a 4. So that's 4.15%. Now we need to calculate the absolute uncertainty of this quantity. So we're not done. So the absolute uncertainty in the quantity pi d squared times t over 8 is this value that we saved from earlier. So 5.61 times the percentage uncertainty of this quantity, which is 2.42 over 100, right? And that's cubic centimeters. So this is going to be 0.4, oops, what am I doing? So 0.14 cubic centimeters. And we will also need the absolute uncertainty in D times X times T, which is this value, 0.63 times the percentage uncertainty in this quantity, 4.15 over 100 cubic centimeters. And this is equal to 0.03 cubic centimeters. Okay, so the let's use another clean page so you don't squeeze everything there. So the absolute uncertainty in the volume is equal to the absolute uncertainty in the quantity pi d squared t over 8 plus the absolute uncertainty in d times x times t, and this is equal to 0.17 cubic centimeters, which is close to what they ask, okay, which is 0.2 cubic centimeters. Okay, this was a difficult exercise in uncertainties, okay? So you have to find problems like this to work out. Watch my video, okay? I think I explain everything in my video on uncertainties. And yeah, just be careful and take it one step at a time so you don't mess up, okay? There's a part C to this problem. So just as if this was not enough, they also included part C. So let's go see it. The student determined the density of the plastic as 1.04 grams per cubic centimeter with a percentage uncertainty of 3%. The accepted value of the density of perspex is 1.18 grams per cubic centimeter. Explain whether the student's measurements suggest that the protractor could be made of perspex. Your answer should include a calculation. Okay, so they give us the percentage uncertainty, so we need the absolute uncertainty in the density, which is going to be equal to the percentage uncertainty in the density times the density itself. So 3% times 104 grams per cubic centimeters yields 0.03 grams per cubic centimeters. So the maximum possible density is equal to rho plus absolute uncertainty in the density, or 1.07 grams per cubic centimeters, which is of course less than 1.18 grams per cubic centimeters, so not perspex. Okay, and this was unit 6 from June 2024. I'm recording this on a Saturday, so I'm gonna abruptly stop the video so that I edit it and upload, okay? Guys, please like and subscribe to these videos, suggest them to friends. I'm trying to grow this channel and make it a community eventually. And I have a research topic that I plan to talk about, by the way. But okay, that's not high school material. It's actually graduate school material. But I want to talk about it anyway because I found it very interesting and fun. Good luck with your exams. Again, please subscribe. And if you want, write in the comments where are you guys watching from. I'm curious. So see you in the next video. Bye.